My name is Dr. Marc Bouwer. I'm an analytical chemist here at Insect Science. I specialize in the field of chemical ecology, and my role in the company is to develop new products and to improve our current products. Basically, what I do is I try and isolate pheromones from insects, and then I try and identify the compounds. So the way we do this is we observe what the insects do. Once we find evidence of a pheromone being present in that system, we then sample the insects. So typically one would take the insects and put them in a dynamic headspace sampling facility, and then the volatiles that the insects produce are then captured on adsorbent material like Poropac Q. These samples are then desorbed, so we use analytical solvents to extract the Poropac, and then samples are generated which are then analyzed on the gas chromatography machine. We typically link a gas chromatography machine to an electroantennogram detector. Basically what that system does is it gives us information about what an insect can smell. Typically one would remove the antenna from an insect and then couple it to electrodes, and these electrodes then measure the potential across the antennae, and while we have that antenna coupled to the electrodes, we then blow the sample of the pheromones over the antennae, and then we record chromatograms and electroantennographic responses from the antenna. And basically what happens is the antenna responds as soon as a compound eludes from the chromatographic column that stimulates the antennae. So these chromatographic peaks are then that give a response on the antennae are then candidate semiochemicals or pheromones for the insect system. After that procedure, the samples are then taken for identification of the pheromone compound. So typically a sample would then be analyzed on a GCMS system, that's a gas chromatography system linked to a mass spectrometer. What that system does, it gives us information about the chemical compounds present in the sample. So basically it's a particle accelerator that's coupled onto a chromatographic column, and the molecules get fractured, and once the molecules are fractured, the particles are then accelerated and detected, and the mass spectrometer then gives us a fingerprint of the identity of the compounds. So the mass spectra that we generate in that system are then screened on known libraries like the NIST or Wiley database library, and then we get tentative identification of the unknown pheromone compounds. So once we have a tentative identification for the pheromone compounds, we then have to synthesize the tentative compound here at Insect Science. The compounds are then used to confirm both the electroantennographic responses of the insect antennae, and also to confirm the mass spectra and retention characteristics of the compounds. Once that's done, we have to then quantify the amounts of the compounds that are released from the insects, and then mimic the pheromone signal artificially in lure devices. So for example, we would place the pheromone compound into an artificial lure, and this is then used to test in the field. So the lure is then placed in a trap, and once we are able to trap the insects in the traps, then we know the pheromone was correctly identified, and then the compound or the pheromone lure can be used for monitoring purposes. There are also different types of application of these pheromones and semiochemicals in the field. We can disrupt insects when we flood the environment with a large quantity of pheromone. So that would be a mating disruption type of control tactic. And We also continuously try and improve the products that we already have, and so we monitor how these lures release pheromone in the environment and quantify the amounts that are being released. In this way, we then know how much of the compounds are being released in the field, and we can then control insects based on an environmentally friendly way if one compares that to, for example, spraying toxic pesticides in the field.